In this video we are going to take a look at a number representation for fractional numbers. The goals are to extend the decimal number representation that we looked at for integers to numbers that include a fractional part as well. And we want to generalize the fractional number representation to representations which use a radix or base of r. And we also want to compute the value of numbers with fractional parts represented by using different r. So let's take a look at some decimal number first. So we will start out with n sub 10, and the subscript 10 again stands for decimal, equal to 3.9672. So the value of this number in decimal is computed as 3 times 10 to the 0, plus 9 times 10 to the minus 1, plus 6 times 10 to the minus 2, 7 times 10 to the minus 3, and 2 times 10 to the minus 4. And we note that there is the decimal point here. And that this is actually giving us the dividing line between the non-negative exponents to the left and the negative exponents to the right. Okay, so 10 to the minus 1, 10 to the minus 2, and so forth are to the right, and the non-negative ones in this case only 10 to the 0, but we could have more here, 10 to the 1, 10 to the 2, and so forth. So we associate this position with an exponent of 0, this position with an exponent of minus 1, minus 2, minus 3, and minus 4. And more generally, we can say that a number representation with respect to a basis or radix r, n sub r here, with digits n sub k, capital K2 minus 1, n sub capital K2 minus 2, and so forth, down to n1 and n0, and then the radix point, and then n sub minus 1, n sub minus 2, all the way down to n sub minus k sub 1, and that's capital K sub 1. So we have here capital K sub 2 digits to the left of the radix point, and we have capital K sub 1 digits to the right of the radix point. And we call the left side here the integer part, of the number, and the right side to the right of the radix point, that we call the fractional part of the number. And each of the digits in here, the n sub little k, are from the set 0, 1, 2 up to r minus 1, where r again is the basis or the radix that we use for our number representation. And then the value of this number, of this n sub r, is computed as v of n sub r is equal to the sum from little k going from minus capital K1 all the way up to capital K2 minus 1. And then n sub k times r to the k, where both of those k's are little k's. The total number of digits that we have is K1, capital K1 plus capital K2. And so, because each digit can take on r different values, namely those values up here, we get altogether r to the k plus 1, r to the K1 plus K2, or r to the K1 times r to the K2 distinct values for the value of that number n sub r. Let's look at some examples, different representations of the decimal number n sub 10, 5.40625. And of course, because we are looking at the value in decimal, that would be equal to that 5.40625. So if we want to represent this in binary with a r equal to 2, a radix equal to 2, then it turns out that this number, n sub 2, has representation 101, and then comes the decimal point, or in this case the binary point, 01101. And we can verify that that is true by looking here at the exponents especially at the exponents of those digits that are 1. So we have an exponent of 0 here, an exponent of 1 and 2. So we have 2 to the 2, then no 2 to the 1, but the next is 2 to the 0. And then we go to the right of the radix point. We have no 2 to the minus 1, but we have a 2 to the minus 2 and a 2 to the minus 3, and no 2 to the minus 4, but a 2 to the minus 5. So we have for the fractional part, so here is the dividing line that we have from the radix point. To the right we have 2 to the minus 2 from this digit here, 2 to the minus 3 from this one, and 2 to the minus 5 from the last one. And we can compute that value and verify that it's indeed what we want it to be here. Or actually, I should say this one here. By saying 2 to the 2, that's 4. 2 to the 0 is 1. Then 2 to the minus 2, that's 1/4. 2 to the minus 3 is 1/8. And 2 to the minus 5 is 1/32. And if you add this up, 4 plus 1 is 5, and then 1/4, 0.25, 1/8, 0.125, and 1/32 is something like 0.0, whatever, 125 or something. It's not 0.0125, but something similar to that. So when you add it up, you're actually getting that 5.40625. So this is indeed the representation, the binary representation of the fractional number with this value here, with this decimal value. Okay, we will look at it also for ternary digits. So in this case, r is equal to 3, and n sub 3 turns out to be 1, 2, and then dot the radix point again, 1, 0, 1, 2, 2, 2, 0, 1, 1, 0, 2, and couple dots here. It turns out that you cannot exactly represent 5.40625 in the ternary number system, so you have to make a close enough approximation, and you just expand it until you are a specified amount away from the actual number. Like in this case, we have 10 to the minus 1, 2, 3, 4, 5. So we would say that if you are within roughly about 1 times 10 to the minus 5, that we are close enough to that number. So we can check here that we get the right thing. Again, we use the dividing line here at the radix point. To the left are the positive exponents, or the non-negative exponents. So 1 times 3 to the 1 plus 2 times 3 to the 0. Then comes the dividing line from the radix point. Then from this one, 1 times 3 to the minus 1, 1 times 3 to the minus 3, 2 times 3 to the minus 4, 2 times 3 to the minus 5, 2 times 3 to the minus 6, 1 times 3 to the minus 8, plus 1 times 3 to the minus 9, plus 2 times 3 to the minus 11. And if you compute the value of that, it turns out to be 5.406250176,407. So it is very close to actually that 5.40625 that we wanted to have. So in general, if you have a fractional number with a finite number of digits in one radix representation, like here in the decimal representation, we have 5.40625, so that is a finite number of digits, then we do not necessarily have a finite number of digits in another radix representation. For example, if you would take the ternary number n3 equal to 0 and then the radix point and then 1, that would mean that this is equal to 1/3. So the value of n3 is equal to 3 to the minus 1 because we have a 1 to the right, immediately to the right of the radix point. And as we know, 3 to the minus 1, 1/3, is equal to 0.3333 forever. In the decimal system, we cannot exactly represent 1/3 in the decimal system with a finite number of digits. Okay, in octal, with r equal to 8, it turns out that our number, this 5.40625, is 5, and then the radix point here, .32. And so we have 5 times 8 to the 0, plus 3 times 8 to the minus 1, plus 2 times 8 to the minus 2. And if you compute that again, that gives us the 5.40625 that we wanted to have. In hexadecimal, we have, of course, r equal to 16. So n16 turns out to be 5.68. Notice that this is very similar to the n8 here, but of course, since the first digit is 5, it's equal to 5 in octal representation as well as in hexadecimal representation. And then the digits after the radix point just happen to be similar, but you cannot usually count on this to be too much similar. So the value here of n16 is 5 times 10 to the 16, 5 times 16 to the 0, because we are to the left of the radix point, and then to the right we have 6 times 16 to the minus 1, and 8 times 16 to the minus 2. And this is again 5.40625 if you use a calculator to compute that. There's another strategy to check such numbers with a fractional part, and that is to actually move the fractional part to the left or the radix point to the right. So if we have the binary number that we had before, the 101, the radix point 01110, 01101, we can move the radix point over here. Okay, and we can write this as 1010101. So now it is an integer number, but of course we have to take into account that we moved the radix point. We moved it by 1, 2, 3, 4, 5 positions, and so we will have to take the value of this one here and then multiply it by 2 to the minus 5, the number of positions by which we shifted the radix point. And so we get what's written down here. And it turns out that this 1010101 is equal to 173 in decimal representation, or in the decimal value. And then we multiply by the 2 to the minus 5, and we get again the 5.40625 in this way. And here is the same thing for the hexadecimal 5.68. So we move the radix point over by 2 positions and then multiply by 16 to the minus 2. And 568 in hexadecimal gives us 1,384 for a decimal value. And then we multiply by 16 to the minus 2, and we get again the 5.40625. So you can choose, when you evaluate numbers, what you find easier. If you have just a finite number of digits in the fractional part, then you can always move the radix point to the right, to the end of the number, and then compensate later by multiplying by r to the minus however many digits you move the radix point, and you will only have to evaluate then an integer number of the particular radix that you're looking at.